If limit x tends to a fx and limit x tends to a gx exist, then 1. Limit x tends to a fx plus gx is equal to limit x tends to a fx plus limit x tends to a gx. 2. Limit x tends to a k fx is equal to k limit x tends to a fx, k belongs to R. 3. Limit x tends to a fx gx is equal to limit x tends to a fx into limit x tends to a gx. 4. Limit x tends to a fx upon gx is equal to limit x tends to a fx upon limit x tends to a gx, where limit x tends to a gx is not equal to 0. Limit x tends to a x raised to n is equal to a raised to n. N belongs to n natural numbers. We shall prove this result by mathematical induction. Let Pn as to limit x tends to a x raised to n is equal to a raised to n. Taking n is equal to 1, we must prove that limit x tends to a x is equal to a. For this, given epsilon is greater than 0, we shall be able to find delta is greater than 0 such that 0 is less than modulus x minus a is less than delta. Therefore, modulus x minus a is less than epsilon. We can take delta is equal to epsilon and the above inequality will be satisfied with delta is equal to epsilon. 0 is less than modulus x minus a is less than epsilon. Therefore, modulus x minus a is less than epsilon. Therefore, limit x tends to a, x is equal to a. Therefore, P1 is true. Suppose Pk is true for some k belongs to n, that is, limit x tends to a x raised to k is equal to a raised to k. For n is equal to k plus 1, we now have limit x tends to a x raised to k plus 1 is equal to limit x tends to a x raised to k into limit x tends to a x. Because Pk and P1 are true, therefore, a raised to k into a is equal to a raised to k plus 1. Therefore, Pk plus 1 is true. By principle of mathematical induction, Pn is true for every n belongs to n. Thus, limit x tends to a x raised to n is equal to a raised to n.